c prime over fy into, then again plus, then again omega, and the value may be less than 1, any number, but it is some finally what here that will have the value which will be 0.85 fc prime over fy. Let me rewrite over here. And just if I assume that the root term what I will get will be like, suppose if even if it is 0.1, so then again 0.85 c prime over fy, because omega is also taken outside. So once I will multiply it within the bracket, it will be multiplied with all terms. So let the answer comes out to be, suppose 0.1 or 0.01, any value, but it will be above 0. So it will not be on the negative side. So this is it means the outcome of rho. And if I now look at the rho B equation is mentioned here. And in this rho B equation, if you look at the answer here, you are getting beta 1 600 over 600 plus fy. So once you will put steel grade in this equation along with beta 1, this shown value second term will definitely be less than 1. And this is omega. So it means omega into a value less than 1 will give you actually the term somewhat which is this one. And in our case, when I less than rho B, it will definitely be greater than rho B. So that is the reason positive root is not selected, root with the positive in between the two components. However, with the negative, obviously, omega will be from omega, the second term will be subtracted. So in this way, we are in a position that the resultant rho can't be greater than rho balanced. So that is the reason we are selecting the rho from the first root of that quadratic equation, which is giving us the under reinforced tension controlled behavior. And I think in one statement it also mentioned the rho will come greater than rho B, leading to brittle failure if we select the positive sign. You can even put some numbers, actual fc prime and fy, assume some values, and then apply this equation with positive root. You will come to know that how it will affect your magnitude. So definitely the answer you will get from the equation within this box, and from rho balanced with the positive root, the answer will be that your rho will come out to be greater than rho B. Now, I think the previous recorded videos are covering this discussion on different type of rhos, starting from rho balance to rho max, and then as well as rho minimum. And I have already discussed in the recorded lecture that preferably when you want to design the beam, you will call this equation to determine the rho, and this equation will give you a direct answer of the under reinforced tension controlled area of steel. And I also have mentioned in the recorded video that rather than memorizing the equation in this format, you may expand this and try to memorize in this shape, because even when I call this equation, when I apply this equation for design purpose, I use this form of equation because it helps me to minimize errors while applying this equation. So I am not using omega here, I am putting the actual value, then 1 minus 1 minus this one, and I actually put actual 2 and ultimate movement demand, which actually R over here reflects that because it has been substituted and it is equal to mu over bd square, and 2.614 also considers multiplication of different numerical values, and resultant answer is 2.614. But if I expand this and I put actual numbers, then it will be 2mu over phi, which will be 0.9 into b into d square into 0.85 fc prime. So this is how I actually use this equation. So answer you will get same. Either you use this in this shape and calculate R separately and then put it inside and then calculate omega separately, but actually 2 over 5 into 0.85, answer will be 2.614, and R is actually mu over bd square. So in this way the final shape will be that you are getting under the root 1 minus 2.614 R over fc prime. So this equation we are going to use quite frequently to design the cross sections. So it is also summarized in this on this slide that in assessment of the cross section, in order to classify the cross section whether it is under reinforced, tension controlled or not, as I have uh, given you one example during derivation of rho max, rho balanced and rho minimum, that once you are given with the cross section and area of steel is also given in the cross section, you will calculate rho of that section by dividing area of steel with the effective area BD, and then compare that cross sectional area rho with rho max. If your rho is equal to or less than rho max, and I mentioned in the lecture that try to memorize rho max equation as well, because it will be very much frequently used in the reinforced concrete design. So rho if in the cross section is equal to or less than rho max, it will be a information that section is tension controlled, and moreover using A and D calculate the strain in the steel bars. The other thing is that if you have the strain diagram, and from that strain diagram you can convert the A into C or C into A, the neutral axis depth into Whitney's uniform stress block depth, or you can convert uniform stress block depth into neutral axis depth, and you can use the equations to determine the steel strain. If that steel strain is 005 or greater, this will again be a indication that section is tension controlled, under reinforced, desirable behavior. However, there is one information given here that if you calculate rho of your cross section, you are with mu, you have the cross sectional dimensions, and mu and b, and you calculate rho from this equation. Actually, now I am talking about the you can say a cross section in which I am selecting some cross sectional dimensions, and I I may say that I have proportioned the cross sections, I have fixed the width of the cross section, effective depth, I have the demand on the beam in terms of movement demand mu in hand, and I want to design that beam. When I will apply this equation, one hint will be that if under the root I will get a negative answer, so it means I'm entering into a complex number under the root minus, or otherwise in our simple reinforced concrete mechanics, this cross section with the terms under the root minus, because the second component 1 minus mu over bd square into phi into 0.5 c prime. So if answer comes out to be negative under the root, this will be a indication that your section is over reinforced, and negative term will appear under the root. So in application of this equation to calculate the rho for design purpose, if you are getting the under the root negative sign, that will be a caution for you that you need to revise the cross section, and in order to get the under reinforced behavior, you need to reconsider the section dimension, because rho what you are estimating will not be the one which will give you rho equal to or less than rho max. So this equation I am going to apply in the design problem, and over there I will discuss this factor again. Now up till now we did little derivations, and in most of them what I have done, I have used equilibrium equations called the strain diagram, and from the strain diagram I have substituted in that equation corresponding to my condition the neutral axis depth, and then doing some simplifications I got different rho values, rho balanced, rho max. So in all those derivations you will find that we are calling basic equilibrium equation longitudinal equilibrium equation C equal to T, and then we are substituting the neutral axis depth corresponding to the required condition, and then we are getting either the rho balanced or rho max equation. So for example, and not in this presentation, in the previous presentation where we derived rho balanced or rho max, you can check later on that we are we are doing, we are calling C equal to T and then putting the neutral axis depth from the strain diagram, and then we are getting the useful expressions. Now there is one more derivation on this slide, which will help us in proportioning the cross section, and particularly in selecting that effective depth which will result into a section which is under reinforced tension control. So this useful expression which we are going to derive will be helpful in designing the cross sections, and while making the design, the first step always is to proportion the cross section, to fix the width and gross H, and then out of that H, subtracting the cover, you will get the effective depth. So which H you will select? Definitely serviceability will guide us, serviceability requirement, that this must be the minimum H to control the deflections. So ACI has given us in chapter 9 in tabular form against various end conditions and steel grades the minimum required H value. So that is actually the first check which we are going to make before finalizing the cross-sectional dimensions. Second most important is this D minimum requirement, that we want to make sure that final selected section dimensions will result into a behavior of the cross section as under reinforced or over reinforced. So this D minimum, you will notice that we will derive in such a manner that this will guarantee us that if I am going with this minimum effective depth, there is absolutely no chance that I will end up with a section which will be over reinforced, which is undesirable. So what we are going to do is, first we are going to select those strains which are ideal, that steel is at point double. So this is ideal new axis or uniform stress block depth and the strain in the steel bars corresponding to failure in concrete. Now what I will do, I will call the C part of the equilibrium equation. So we know C is equal to T. So I am writing the internal capacity equation with the compression force into lever arm along with the capacity reduction factor. So rather than using T into lever arm, I am using C into lever arm with the capacity reduction factor phi. And since we are looking for under reinforced tension control, so I am putting 5.9. CC, you are well informed that CC is actually, using Whitney's simplified theory, CC is 85% FC prime into the area on which these uniform stresses are present, A into B, and the lever arm between these force C and T is D minus A by 2. So I am just substituting CC and LA with their corresponding values. and I'm making this internal capacity ultimate movement resistance my demand, external demand mu. So on the right hand side is the internal ultimate resistance, and on the left hand side is the demand. So for economical design, I'm making them equal. Demand is equal to capacity. For now I am putting that typical uniform stress block depths in A, which will ensure crushing in concrete corresponding to 0.05 ductile behavior. So I am replacing this A with that value, which I know from strain diagram that this will be beta 1 3 over 8D. So once I substituted that and simplified it, I got this simplified right hand side 0.205 FC prime B into D. I will keep D on one side and will bring other variables on the right hand side. So this equation then will tell me that if I want crushing in concrete corresponding to 0.005 in steel and a neutral axis depth which is ideal, that is 3 over 8D or A beta 1 3 over 8D, then this must be the D of the cross section against a demand of mu for a cross section with width B in a reinforced beam with concrete grade FC prime. So it means this is the minimum D which will make the left hand side equal to right hand side, demand equal to internal capacity, and further the capacity I am calculating with that neutral axis of concrete. So if we keep in our selection of the cross section for design problems, D of the cross section greater than or at least equal to D minimum, the resultant section will be tension controlled under reinforced, and it means that section is stronger in compression, or in a way I may say that steel will yield first, it will yield excessively, and then finally concrete will crush. So in design problem you will notice that we will be using this equation in order to select the section depth. Now with this you can say discussion regarding tension controlled under reinforced cross sections which are ideal for us, during the capacity analysis there are chances that we may get a cross section which is over reinforced. It means that when concrete will crush, steel is below yield strength. So in over-reinforced failure, what will happen if we categorize the stages? Stage 1 will be just like any other reinforced concrete cross section. That stage 1 will be section will be uncracked. T will be equal to C, and T will be given by steel and as well as concrete. Although concrete contribution will be small, but since section is uncracked, so the tensile strength will be contributed by both steel and concrete. Then stage 2 will be section will be cracked, and as you have seen that in when under reinforced sections, tension control sections, this is just like the same stage, that modulus of rupture will come and concrete will crack in on tension side, and now the steel is contributing in developing the tensile force. So C is still equal to T. Then comes the stage 3, that concrete reaches the strain of failure, ultimate strain. But at that instant, steel is not yielding. It means stress in the steel bar corresponding to failure in the concrete is so stress in the steel bar corresponding to failure in the concrete is below Fy. So for this compression controlled or brittle failure, phi then will be 0.65. Capacity reduction factor will be very strict. Now if I have this behavior of cross section, that concrete approach its failure strain but steel not yielding, and I want to determine the capacity of that cross section, again I have the option that I will be calling compression force into lever arm or tension force into lever arm, because equilibrium means C is equal to T. But now in this case, T is not ASFY, T is ASFS, because section is not, steel is not yielding, and C is 0.85 FC prime B into A. So for over reinforced behavior, I am selecting C into lever arm along with the phi 0.65, and I am getting again the equation of internal resistance Cc into lever arm. The problem is, unlike tension controlled under reinforced cross section where we have derived from the strain diagram that A will be beta 1 3 over 8D. So from strain diagram we can easily get this expression. Now since section is not tension controlled under reinforced, A I can't use equal to beta 1 3 over 8D. It is, since it is over reinforced, and in my strain diagram it means when concrete will be at 0.003, crushing in concrete, steel will be at some strain epsilon s, but its mechanical value is not known to me. If it is 420 grade steel and it has yield strain 0.0021, but since it is over reinforced, I'm not sure at that instant the strain is 0.001 or 0.0015 or 0.0019 when concrete crushed. I know that it will be less than yield strain, but its exact mechanical value is not known to me at the moment. If it is not known, I can't fix the C value. I can comment like this that C will be greater than C max, or I can comment like this: C will be greater than C balanced, but I have no idea how much mechanical value will be. So in order to determine this capacity, A will become a challenge for me, that what A I should put here. It is unknown. Since epsilon s is not known, so Fs value is not known to me. If it is grade 420, I am not sure it is at 200, 300, 350, what stress. So what I will do, I will write the equilibrium equation C equal to T, and in that equilibrium equation C equal to T, I will keep A on one side and I will bring other variables on the right hand side, and that A I will substitute here. So then what I discussed on the previous slide, from strain diagram I can also B minus C, I can also draw the strain diagram of this over reinforced cross section just like this, that corresponding to crushing steel is at epsilon s, and from similar triangles I can write this equation, and after simplifying this equation I can bring epsilon s on one side, and I will get on the right hand side 0.003 beta 1 d minus A over A. But this A is not known to me, so I will keep it as unknown, and I will call the Hooke's law, and I will calculate Fs by multiplying this strain with modulus of elasticity, but still I will get Fs in terms of A, function of A, because A is still not known to me. I can put beta 1 d, but A will remain as unknown. So this Fs I can substitute here in equation 2, is done here. And when I will replace that Fs with this equation and I will simplify this, I will get from equation 5 a quadratic equation in terms of A square plus BA plus, you may use any alphabet like let it be Y equal to 0. Even in you may get confused with this b. This b is not actually the width of the cross section. I may use xa, any coefficient with a. So once you have this quadratic equation, you will get two roots. One root will be positive and other will be negative. So distance can't be negative. So you will select the positive from that quadratic equation and then use that a to determine the capacity of the cross section, either with C into lever arm or T into lever arm with 5.65 and calculated Fs from this equation. If you want to use T into lever arm, if C into lever arm, fine, your calculated A will be used here and you will get the internal capacity. So you will notice that in order to determine the capacity of a over-reinforced cross section, you need to do little hard work, because you need to first establish where is neutral axis depth, and you need to derive a quadratic equation, get the A, and then you will be getting the internal capacity. Unlike under reinforced cross section, in which very quickly we can determine the capacity, because AS Fy and the lever arm is d minus a by 2, and A we are knowing it is beta 1 3 over 8 d. So answer is quite quickly available, and section is also desirable. Behavior is also desirable, and analysis or design is also very simple. Unlike the over reinforced cross section, in which behavior is also undesirable and its assessment is also difficult, because we need to fix the neutral axis depth and then we need to determine the capacity based on that calculated A value. Because once you calculate the A value after doing this exercise, you will calculate epsilon s from this equation, and definitely the epsilon s will come out to be less than epsilon y. That will be a hint that your calculations are on the right track. So if there are some type calculation errors, you will be cautioned once you get epsilon s and it is not according to the well-known behavior that in over-reinforced cross-section, epsilon s will be less than epsilon y. So this is how we will be dealing with the over-reinforced cross-sections. Now let me discuss one problem online. So if I ask you to design a beam, so my statement is that I am asking you to design a beam, not to analyze a section. Design a beam of span 6 meter and beam is simply supported, single span beam. And beam is subjected to a ultimate load of 75 kilonewton per meter. WU is given to you. It is 75 kilonewton per meter. Beam is 6 meter span. Simply put. Furthermore, I propose that in this beam, concrete will be of grade 20 megapascal, 28 days cylinder strength at the average of 2. Standard cured cylinders tested at the age of 28 days, and average of 2 cylinders is reported as FC prime, and Fy 420. So this is my question directly asked, that you have to design this beam for grade 20 and 420. So I'm asking you to design this beam. The first I should select. Question 1. Question 1 is to proportion the cross section to fix the B and H. And then finally once done, to select the steel bars, stretch it properly, how much of grade 4 to pick design or so now table from spotted end condition and steel grade 420 beam simply spotted. What was the serviceability requirement of the beam depth to control the deflections? So just let me know from that table. Open your notes and anyone can respond me by answering that how much.
Excuse me.
Yes, please.
Sir, it is L over 16
L over 16.
or simply spotted 420. Yes, sir.
Sure. Anyone else with a different view? I will advise all of you to please open your slides or notes or actual ACI code and let me know the answer given by your fellow is right. Span by 16 In this way it will be 6000 over 16. So how much it will be in millimeters?
375 millimeters.
375 millimeters is the H value proposed by the code to control the deflections. So you can't go below this until or unless you have some strong justification in terms of your calculated movements, and you can prove that this will give me the deflections below proposed by code, then code can allow you to go below this H. In absence of those sound calculations, there will be a restriction from code that this minimum H must be executed, otherwise deflections service loads will exceed the serviceability requirements, and a sagging beam will not be acceptable. So this is one, you can say, guideline. A trench with the steel plates, and within that will also be important, and normally multiple of 3 inch or 75 millimeter is commonly used, and we start normally from 9-inch brick, masonry brick. Uh, you can say clay brick. If I am a trench made up of Please close your mic. So if I want to estimate at this stage that what finally will be my cover in the beam from soffit to the center of the steel. So first I will take 40 as the clear cover. Then at this stage, if I assume that my rings, ties, shear stirrups, which will be our next topic of design, are of dia 13 millimeter, rings which are used to resist the shear force. If these ties dia I assume is 13, and I also assume at this stage, because my design is not yet complete, this will be my final decision what should be the dia of the bar, but I can safely assume on the conservative side that the bar dia will be 25. It is my assumption. So half of this will then be 12.5. So I can state that cover from bottom edge to the center, which must be added in D to get gross H, will then be 53 plus 12.5. How much it will be? 65.5. 53, 63, 64, 65, 65.5 mm. Even if I round it up and I assume that my cover will be 75 millimeter, round up will be safe, round down will be unsafe, because if I will finally during execution I will make the cover more than 75, it will affect my effective depth 525, because in gross H I have selected a cover of side. I am selecting a cover of 75. D minimum I have estimated 525. So as a whole, H I got 2 fit 600 millimeter 2 fit beam, 2 fit deep, 600 millimeter deep beam. So it is 1 fit by 2 fit. In civil department, you have seen most of the beams are quite close to this dimension, 300 by 600, 1 fit by 2 fit. So it means decision is made regarding the section, that beam what we are going to use will be of dimension 300 by 600 with the effective depth 525. Now it is the time to determine the reinforcement ratio in this beam, which will give us tension controlled under reinforced behavior. For that purpose, I recommend you that if you are following this flow chart, what I'm following this design problem, you will quickly get your design done So I am following this row equation which we have derived few minutes ago. I have discussed this equation. I am putting it in this form, and I suggest you to keep this equation in mind if you want to become a good designer. Its derivation and its final shape, pi BD square into 0.85 FC prime. Now this equation will help us to determine that row which will qualify crushing versus a steel strain in the steel greater than or at least equal to 0.005. The reason is I have selected the D value using that A. In derivation of D, you have seen we have substituted A of this strain diagram, 0.003 versus 0.005. So I have not compromised on the effective depth. I even rounded it up to 525. And after selecting the cover, I have proportioned the cross section. And now I am calling this equation to get rho. So mu is 337.5 into 10 power 6, 5.9, B 300, D 525 square, and FC prime 20. So please tell me final row value. First check that under the root whether you get negative sign or positive sign. So if you get negative sign, it will be a caution that you are actually leading towards a over reinforced cross section which is undesirable. Everyone should calculate and please participate. जो भी online है, I suggest all of you to please do this calculation at your own. You can develop a spreadsheet on Excel with such useful expressions and try to design the cross sections quickly by calling these equations present in different cells of Excel sheet. So will you give me one by one answer that first, what is the answer of this ratio 2mu over pi bd square, और या इकट्ठा पूरा ही रो बताएंगे?
सर ये कंप्लीट अंडर रूट की वैल्यू 0.683 आ रही है.
ये कंप्लीट अंडर रूट की? ओके ओके फाइन, ओके फाइन, ओके मैं इसको ओमेगा ही लिख लेता हूँ और 1 माइनस, और आप कह रहे हैं इस अंडर रूट की वैल्यू आ रही है 1 minus this term
0.683.
मैं ठीक लिख रहा हूँ 0.683.
जी सर.
This is what you are saying. Agreed. ठीक है, आगे निकालें फिर 1 minus 0.683 into ओमेगा जो कि हमने 0.85 C प्राइम और Fy से उसको रिप्लेस किया हुआ है. And let me know
सर कंप्लीट वैल्यू है 0.0128.
good 0.0128. So at this stage there is one very important cross check. You got this row and now you can use this row, you can multiply this with B into D to get area of steel and your design is over actually. Once you got the row, you can use the basic equation, that is AS rho is equal to AS over BD, and then you can multiply this row with BD, you get area of steel. That's it. But now it is the time to cross check that whether your row is greater than row minimum and is less than or equal to row maximum. Now since you are doing the design, you want to make sure that you are designing a ductile, tension controlled, under reinforced cross section, and which domain you are actually selecting for your cross section. Since you have used 5.9 over here, so your row should be maximum equal to row max or less than that, and it should be above or minimum equal to row minimum, because if that is the range, your design will be up to mark. So sorry, so let me keep the and let me add one more slide here. Now again, as I said, it is the time now to check that this row calculated where it falls. You remember that we have done this very useful derivation, that what is row max. I have shared with you recorded video derivation of this row max. It is 0.85 beta 1 3 over 8 So this is the row max equation. In this presentation, this row max equation derivation is not available in the let me open for your reference. This was row balanced, then this was row max. If you recall, we have done this derivation 0.85 beta 1 3 over 8 into fc prime over fy. Now let me take you to that equation. What is rho max for the concrete grade 20, steel grade 420, which we are using in our cross section? Beta 1 for concrete grade 20 will be again 0.85. So what will be the rho max? 0.0.
Sir, it is 0.0129.
129. Since I have selected very close to what D minimum was suggested by that equation, so that is the reason my rho is very close to rho max. I may call it rho design, which is 0.0128. And now I want to check what is rho minimum. For rho minimum, we have the code proposed equations under root fc prime over 4 fy 1.4 over fy. So from the first, now fy is 420. So from first and second equation, how much rho minimum you are getting? Be 20. Please tell me.
सर पहला वाला है 0.0027
Good.
and
Now please check again. 0. Sorry, repeat. 0.00.
27
Fine. Okay. And second one.
0.0033.
Good. Agreed. Right. So it is 0.33%. Rho max is 1.29%. And what we have done, it is 1.28%. So there is a good news that we are successful in designing a rho which is less than rho max, ideal. Sorry, there was a connection issue at my end. So now I am reconnected. So are you there?
Yes, sir.
Okay. Oh, good. So in a way, I am successful that the rho is below rho max and it is above rho minimum. Now there is one more additional check which is important just for your cross check I want to share here. As a matter of fact, design is now complete because we have established that rho is within the domain. I am rightly selecting 5.9. So as a matter of fact, now I am allowed to calculate area of steel because my area of steel will be equal to rho BD. So I can simply write here that AS will then be rho into B into D. So I have no issue with putting 0.0128 here, multiplying it with 300 and into the effective depth 525. So in millimeter square, can you tell me area of steel?
Sir, 2016, 2016.
Good, 2016 millimeter square. So obviously, once you will consult the design for the nominal sizes, I have shared with you ACI document, and in all textbooks you will get design tables, nominal areas of US customary bars. In selection of bars, please make sure that you need not to round down. You can't select area of steel less than 2016, but you can't go too much above 2016, because if you will select area below 2016, you are under designing the cross section. Not acceptable. Less than rho max. Don't round up to that degree that you enter actually the transition domain, because if your rho will come out to be greater than, you are already very close to 0.0129. So now it is your task to let me know that in a cross section of width 300 and a cross section of width 300, you can safely put 4 bars in a row without violating code instructions. 4 bars you can put in one row. So I will discuss why 4, why not 5. So first tell me what bar size you will select. Just open ACI code or your design book by Z.A. Siddiqui or McGregor. You will get nominal areas. For example, what is the nominal area of number 25? US customary bar. Its area is 510 millimeter scale. Are you there? Are you listening?
Yes, sir.
Okay, then if I select 4 number 25 bars, how much area I will get?
204 is
2040. Perfect. So I think this is the most ideal selection. We are lucky enough that we are getting the area very close to what we desire, and rounding up is very small. So even if I want to now check that in my actual section, which I will execute, my area in the cross section will be 2040, and divided by if my cross section will have the effective depth as calculated theoretically that it will be 525. So then how much rho in actual beam will be 2040 divided by 300 into 525.
0.0129.
Good. So it means even if I have done some rounding up, and although in selection of this D I am little generous, because actually strictly speaking you recall that we are getting as per the code fulfilling the clear cover and other requirements, strictly speaking at site in the formwork when I will place the steel bars within the cage of ties with a cover of 40 millimeter below the ties. So theoretically and even practically at site, if I am very much careful during execution, my cover will be 65.5, and out of 600, when I subtract 65.5, my actual cover at site, I will get D more than 525. So strictly speaking, I may say that 600 minus 65.5. So realistically, I have even the D, how much?
534.5.
ये आपकी आवाज बहुत कम आ रही है, थोड़ा लाउड बोले.
Sir, 534.5.
Good. So in actual, it is very close to 534. So in that way, my rho will further drop, and I am not worried with reference to the actual conditions in field. I need to worry if I have the covers at site by mistake, or in a way if I end up with more steel layers. Here I am so lucky that I am ending up with one steel layer and I am fitting 4 bars in one layer. Why? I will tell you in a few minutes. So at the moment I am quite lucky because my cover assume and my cover in field actually are all supporting my design, and I will be even more safe if at site they are providing 65.5 cover, because it will even increase my lever arm. It will make my internal capacity even more what I am theoretically calculating. But its vice versa is dangerous, that I am selecting 525, but actually at site I ends up with 535, with 5, you can say a cover of suppose 500 or 515, sorry, effective depth of suppose 500 or 515. Any effective depth less than 525 is dangerous, because it will result into a compromise on my capacity, because my lever arm will be affected and as well as my rho will increase. So this is what I want to explain, that while making a final sketch, you must be very careful that how you place the bars in one layer, what actual covers are in field versus your theoretically calculated on paper. And while visiting the site before concreting, if you are doing a top supervision as a designer, it is your responsibility to make sure that according to your calculations, covers are provided in actual beams. If they are compromising on your and you need to implement the compromise on the covers. If cover provided less dangerous because it means your fire rating will be affected. You affected your if you, otherwise they in the bars is less than 25 millimeter. Largest bar dia, so if bar dia is 25, so it means in our case 25, and 4 by 3 of the coarsest aggregate particle. So normally in our concreting we use 3/4 inch down concrete, 3/4 inch down coarse aggregate, sorry, जिसे हम कहते हैं pony का size 3 by 4 inch. So code has a clear recommendation that out of 3 the larger will be selected as a clear gap between the bars. So it means in our case we have a direct recommendation 1 inch. There must be a clear gap of minimum 1 inch between the bars. The largest bar dia, the clear gap between the bars should not be less than the largest bar dia. In our case, incidentally, both are equal. Third is 4.3 times the coarsest aggregate particle, because if you will have a clear gap less than this, your coarsest particle cannot flow through the gap. So in your cover concrete, quality of the concrete will be compromised if bars are closely packed. So once you will open the formwork, you will find that in the cover concrete, quality is compromised because the coarsest particle was unable to flow through the gap. So there is a recommendation that 1.33 times the coarsest aggregate particle should be the clearance available between the bars. So in our case, what would be the governing clear gap, which will govern 4 by 3 into 19 govern करेगा या 25 या 25? Are you there?
Yes, sir.
जी प्लीज बताएं which one is.
सर ये 4/3 × 19.
इसका आंसर कितना आता है जी?
Sir, it is 25.33.
Okay, you are very close to 25. So let it be. If we are very much mechanical, it means the clear gap between the bars should not be less than 25.33. Furthermore, like the bottom clear cover 40, the edge cover recommended also is 40. So in a beam, it is mandatory that the corner bar, if it is enveloped by the ring, so not only the bottom cover but the edge cover, code recommends it should not be less than 40 millimeter, 1.5 inch for interior beams. Equal to or less than 300, 2 into 40, both sides edge cover 80, 2 into 10, 20, it becomes 100, 25 into 4, it becomes 100, 25 into 3, it becomes 75. So in a way, I am ending up with a dimension of 275 millimeters if I am putting 4 bars in one layer with 3 gaps of each 25 millimeter. So as you have said 25.3, so even if you make it 25.3, so 3 into 25.3, or if you say I have a tie of dia 13, so 13 into 2, so still your answer will remain well within 300 millimeter. So that is the reason I have selected 4 bars in one layer in a beam of width 300 millimeter. So it means this final sketch will be approved, and if this will work in actual beam, once you will sketch, your effective depth will even increase, and so strictly speaking, when I will sketch now with these selections, so I will have 4 bars. If they are enveloped by number 10 ring, so I am actually getting then 40 plus 10, 50 plus 25.2. So strictly speaking, if my shear design that your tie is number 10 is okay, not number 13, so then you even have a cover of 62.5. It means out of then 600, your D will be then 600 minus 62.5. So you are even more happy that you are getting more effective depths. So it all depends that where final your shear design and sketch will be done and finally executed at site. So you must be little conservative in your initial selection so that later on, if there are some compensations to be done, then you must have a little cushion available. Otherwise, you need to revise your design. If I am in start very much unconservative in selection of covers, then finally while making sketch, if I am getting effective depth less than 525, I must be worried. But now I am happy that my final effective depth is even more than 525. And this is now the final design in which even your row, now if you calculate the row, your row will be even further less than row max, because the denominator d will further increase. Now one more point which is important, in your cross section which you have designed and finally sketched, if you want to check what is epsilon s in the steel, or where is the neutral axis depth, you can even calculate that. Although this is one additional step, but just to let you know that even if you are doing a design problem and you want to know that in your design cross section what will be epsilon s corresponding to failure in concrete, you can do this with little effort, because you have the basic equation with you, T equal to C, and now since you have finalized the rho value as well, and you can very easily calculate the C value. From that C value, you can calculate the epsilon s, and that epsilon s definitely will be greater than 0.005. So this additional step, which is not actually part of your design because you already have classified your cross section by this condition that your row is below row max and it is above row minimum. So in that way there is absolutely no doubt that your design is perfect. But still, if you want to check that in your cross section corresponding to crushing in the concrete, what will be the strain in the steel bar, that you can do very easy. What you need to do is you just need to write the equilibrium equation. From that equilibrium equation, AS Fy equal to 0.85 Fc prime AB, you will get A. From A, you will get C. From C, you will draw the strain diagram. And from similar triangles, you will get epsilon s. And definitely it will be greater than 0.005 if you have not made any mistake in your design. And you already have this confirmation by comparing your row with row max. So I think while solving this problem, I tried to cover all the aspects which are important in finalizing the design. So in next lecture, we will be discussing the load transfer path and more comprehensive design of the beams by considering the load estimation on the beams as well. So I again suggest you to please keep watching recorded lectures in advance, otherwise you will not be able to get 100%. Your exams, whenever they are scheduled, there might be midterm, end term, or I'm not sure how it will finally be decided, but that PRC1 is little lengthy, not difficult, but it's lengthy. But and if you will not be following the routine lectures, you will not be able to finally cover all the topics in your exam. So up till now, we only discussed beams, rectangular beams, and allowable stress and ultimate strength design. So please follow all the recorded videos. So this video is also being uploaded, so you can check this in the files folder.